almost always. I feel really guilty if I don't go to class. Even if it's the situation where I go to get a drug test, it turns out I don't have my drug test, and then I'm sitting there for an hour waiting to get a drug test. God, this is such a crapshoot. They still haven't tested you yet?
No, I got it.
Okay. Good.
Kyle, you're a junior.
I am in my third year here, yeah, but I graduate in May, so.
Oh, nice.
I'm
Where?
I don't know what you would call it.
You're a senior.
I'm a senior.
You're a senior.
But I'm in my third year.
Super junior.
It's super junior.
Yes, thank you. Oh, God, look at this.
That was more so for me,
Yeah, it's so pretty.
to see
Yeah.
that they were all the same.
So lovely. All right, well, it's the three of us.
Usual crap.
The usuals, yeah, the regulars. Did you get a chance to read anything about cosets?
Yeah.
Cool.
Well, I read what I was supposed to.
Yeah, fair enough, fair enough. Cool, so, let's just maybe go together. We're gonna do a lot of computation today. And I don't really have an assignment rigged up for you yet, so bit of a reprieve, tiny reprieve. Which will be fine, I'm sure, right? Yeah, is that okay? Okay, all right. Awesome. Got G as a group. H is a subgroup of G. I'm going to take some element out of G. What's this? What's it called, and then what is it?
The left coset of H and G containing A.
Yes, yes, beautiful. So it's the left coset. A left coset, but it is the left coset of H and G corresponding to A, which is an element of G. Cool. What's this? Oh wait, let's go back. What is this then? Like if I were to write out a set notation, what is that?
A little h.
What was that you said? I'm sorry.
A little h, not
Yeah. And then what is H?
an element of h.
Yeah, so it runs over all the elements of H. Yeah, absolutely. I'm going to start like a picture that we'll take a look at in just a little bit, or get into when we get into Lagrange's theorem. So if I have this group G, let's say we have a subgroup H here. We know that that has to have an identity element. So that H has the same identity element as G, because it's subgroup G. And then we take some element outside of, well, it doesn't necessarily have to be outside of H. So let's just keep that picture there for a second. Here's a cool question. Is A an element of H? Just ask some questions about this. AH, excuse me. Is A inside there? These are warm-ups. Yeah, why is that?
Because it's one of the properties of cosets.
Ah, yeah, cool, okay, that's a very legal answer. Yeah, it's true.
It's like the first thing that's written under properties of coset.
Hell yes, absolutely.
Yeah.
Why? What's the proof without looking at our books?
Huh.
Why?
That's
Right up here, eyes up here.
Because
That's what I did for my reading on Friday.
It's okay, we can figure this out. So, there's some hints up in that picture.
it's little h
Yeah, actually, because this runs over all the things in H, and we know that E, the identity element, is in here, right? So we know that E is an element of H. The identity for the group, it has to be, because this is a subgroup. So taking a look at all these pairs, so AE is also an element of AH, which says that A is in there. Does that make sense?
Yeah.
Because basically you can take E out of here, right?
Yeah.
And you get that. Very cool. Is HA necessarily, so take some H in H. Is HA an element? Sorry, my writing to go question mark. Thought, no, it was okay. I thought Diana came in or something. I was like, oh. But then I was happy to see you too, so it's no disappointment. It was like,
It was disappointed it was only you.
She knows I love her. Is this in general true? Take some H out of H. And let's say so H is an element of H. Can I say this is a general property? Here, let's write it out. So is it? Not necessarily, right? Why is that? Yeah, it may not be abelian. If G is abelian, then we can swap things, then this would be true. So this is not necessarily. If G is abelian, then yes. And if G is abelian, then actually, what do you call this thing here? Right coset, yeah, nice.
Good job, Kyle.
Friday. So this is the right coset of H, G corresponding to A, and when, oh yes, lovely. What a day it is. It's a good Monday. When would this be true in general? This is true if
G is bounding.
yeah. Otherwise, it's not necessarily going to be the case. We'll look at that. We'll look at some solid examples of that today. All right, so that's just a little bit of more about thinking about these things. Let's do some computation. So I'll come back to this picture. All right, so let's do a bunch of examples. So we got G is Z6, that's friendly, that's manageable. And then H is, this set is that a subgroup? What is our op first off? What's our op? Operation. Plus, yep. Plus. Is this a subgroup of G? Right, yeah, it's close to under addition, right? 2 plus 2 is 4, 2 plus 4 is 0, 4 plus 4 is 2. All is good, and this is all nice and abelian. Let's just make some notes of the happy things we have.
Imagine just somebody else watches this class, they hear 4 plus 4 is 2.
Like what do they think?
Without knowing the background
And you're all
of the
taking
class.
notes.
They would definitely not
Just
think
some
about
random
math
person
teachers.
watches the video, 4 plus 4 is what?
I guess it is. Whatever you say. So we got a subgroup of G, in fact, a proper subgroup. So I'm kind of taking off that possibility of equals there. Let's write out all the cosets. So all the cosets of H, G, and that means I'm going to find 0, H, I'm going to find, right, because that's my, let's write out what everybody looks like here. That, I have 1, H, 2, H, and I'm writing this with a multiplicative notation, but what actually is happening here? Is this times? So for cosets, what is this just 0? Because it's 0 times everything? What is the operation that's implied here?
I thought multiplication sounded good.
It does, like in that general abstract algebra sense, so legally, you ain't wrong. Can we be more specific? So, can I multiply in this group? Is this group closed under multiplication? No, it's addition, right? It's plus. So when you see this, so here for an additive group, this means A plus H. That's our operation. So this implied operation here is the op of G, whatever that is. So that means these are all pluses. We can just put them in there and feel a little more confident about what all these are going to look like. So let's get them all mapped out. Do some sanity checks up here for us. Wait. No. Yes. Yeah, yeah. Feel good on this. Yeah. Does the order in which I wrote some of these things matter? They're just sets, right? So these are just sets. So order is unimportant. How many actual different cosets are there? There are just 2. So check it out. There's really only 2 different sets here. There's 0, 2, 4
Oh,
in different orders,
yeah.
or 1, 3, 5. So here, there are only 2 different subgroups. No, don't call them subgroups. 2 different cosets. And we could say left. Just a little in parentheses. Here we have an abelian group, so left and right cosets aren't going to be different. But just to be precise, of H, G, and those cosets. You can just pick any one of these as the representative. So let's say we've got 0 plus H, and then 1 plus H, and that's it. Just these 2, and everything else turns into one of these. What's the order of H? Let's just note some things. What's the order of H? 3. How many different subgroups are there? 2. I mean, it's not subgroups, cosets. Number of different cosets equals 2. What's the relationship between those numbers and the order of G, the group, the main group? So how do these 2 numbers relate to the order of G, the order of the main group? Yeah, exactly. So this number here, let's actually just label it now. They label it a little bit later in the book. This is denoted as G:(H). and it's called the index of H in G, and it's actually equal to the number of cosets, number of distinct cosets. So we start to get this inkling. Let me get this out of your way, Diana. We start to get this set here that it seems like, and we're not going to claim this yet, but it does seem like the order of G is equal to the order of H times the index of H in G. At least here, anyway. Seems to be the case. And here's a slightly more interesting way to write that. That the index of G and H, the number of distinct cosets of H and G, is the order of G divided by the order of H. This is going to turn out, I don't know how far you read, this is going to turn out to be a thing called Lagrange's theorem that we're going to prove in general, but we're seeing it manifest here. So one thing I want a couple of things to note. Are these, any of these subgroups of H? I guess this one is, right? This is a subgroup, of G, I mean. Yeah, so this is actually a subgroup. It's closed under the operation. What about this one here? Is this a subgroup? No, just give me one reason why.
5 plus 1, mod 6 is 0.
And that ain't in there. Yep, absolutely. 1 plus 1 is 2. This is another one for the people coming by. Okay, everybody, 1 plus 1 is
2.
2. Woohoo! Class is dismissed. And that's not in here. So note that cosets aren't necessarily subgroups. In general, I would say. Subgroups.
They are subgroups or not?
Are in general not. Thank you. Not. Thanks, Sydney.
Of course.
You'll be my lawyer, because you've been legal this morning, so I need a lawyer. I need someone to represent me. My wife does it in outside of school, so you can be my lawyer here.
What about the law here?
Yeah, the math law.
Sometimes. Sometimes math law.
It's the only law to worry about, really.
Sometimes I like to pretend I can break the math law rules.
I think we all do from time to time.
As we should.
Yeah, I mean that's how we learn new things, right?
That's how I learned that I can't break the math laws.
pushing the limits of the law. Alrighty, let's do another example. Let's make it a little bit more interesting. Let's go somewhere non-abelian. So, oh, indeed. So I think we'll go to S3. So it's not too exciting. So let G equal S3. Collection of all permutations on 1, 2, and 3. And let's let H equal the identity. I want to make a comment about that really quick, but so in S3, the identity, so let's just make a little note here. In S3, the identity, we use an epsilon for that, because kind of like that Greek lettering system for our permutations, is the thing that just fixes everything. Right? It doesn't change, it just, everything gets mapped back to itself. Notice that that is also, can be written as disjoint cycles. 1 goes to 1, 2 goes to 2, 3 goes to 3. But we need to have some kind of thing for it. So we could put an epsilon here, but just simply noting one of these means the other two are that way. So we could do this, just really indicate one of those. And remember that unspoken permutations are identities.
So that's why there's just a 1 here, just to let us know. 1 goes to 1, and the other stuff must just map to itself. Is this a subgroup? Just a quick check. Yeah. Oh, there's only one non-identity element in it. What is the order of this? Tea time? What's the order of this? It's a cool little table. What's the operation? Composition. Yeah, composition. So identity doesn't change anything. What's 2-3 composed with 2-3? Three composed with 2-3. What does it do to 1? Nothing, just leaves 1 alone. What does it do to 2? Sends it back to 2. 2 goes to 3, which then goes to 2, and then 3 goes to 2, which goes to 3. What's the order of 2-3? Compose it with itself once, which is that basically it's 2-3 squared. So the order of that is 2. And you can see that if you just crank this out right here, got a nice little Cayley table for that subgroup. You can see it's totally closed. The only element besides the identity has order 2, so it's a tiny little subgroup. It's a good little friend for us to work with as we go through and find every single coset of H in S3. So let's write up what all those possibilities would be together. So the first one is we're going to have identity times H. We're going to have 1, 2. Let's do 1, 2. Times H, let's do 1, 3. Times H, I'm just gonna list all the transpositions first, and I think that's all of them. It seems like all the transpositions, doesn't it? I can't imagine there's any others. And then we've got 3 cycles. This is order 1, order 2 stuff. 1, 2, 3, H. Remember, that's 1 goes to 2, 2 goes to 3, 3 goes to 1. What's another 3 cycle?
3, 1, 2.
Is that different?
I'm not sure.
That's the same thing, right? So it's rotation of this. Notice it still sends 3 to 1, 1 to 2, 2 to 3. So what do I need to do here?
Flip 2, 3.
We can flip a couple things. Yeah, get them in a different order. There we go. And then what else? What's another? Yeah, I heard that whispering.
Oh.
So 1 goes to 3. What is this different though? Hold on, let's check.
Know.
We gotta check. So 1 goes to 3, 3 goes to 2, 2 goes to 1. 1 goes to 3, 3 goes to 2, 2 goes to 1. Yeah, I liked it. I liked the thought. That I was thinking that too. So flip 1 and 2, something like that. Does flipping 1 and 2 get us something new? 1 goes to 3. Nope. Shit. 2 goes nope.
I can't see another one.
Yeah.
There isn't. If we flip.
It's the same as the one above it, isn't it? It's the same, as the one right above it.
Yeah. So we know that there's got to be one more because how many elements are in S3? 3 factorial. So that's 6. So there's one more that we're not getting.
There's 6
There's
there.
6 on the board.
Are there?
Yeah.
Oh shit, look at that. See, I do need legal representation. Thanks. This is again, how many things are on the board?
I promise we have pictures.
So now we have to do a little bit of computation and write out these various sets. So let's do that. And remember, it's you're composing this on the left with each thing in there. And doing it with the 1 is gonna be easy. So you get a free one. Each one of these things is in that. Okay, I know what a 33 is. Excuse me. I wanna just do it once, at least together. I wanna do the right cosets as well. Just so we say we've seen that, done that. And this is pretty soothing, given the things a person could be doing on Monday morning. if you get done, what is the order of H and G using left cosets? And if we used right cosets, is that the same? Did that change? In agreement, Kyle? Seems like, yeah. What'd you get for this? 3. Let's let everybody else spin, wrap it up.
Where does that come from?
Ah, yeah, good question. This is the number of left cosets, distinct left cosets of H and G. Notice that there's only 3 different things that actually occur up here. So. And did you get the same thing for right cosets? Yeah. And that's good. We should. Anything interesting to note about left cosets versus right cosets? Is the left coset of 1, 2 the same as the right coset of 1, 2? No. So because this group is not abelian, in the end, we get the same information. Notice that we have the same collection of things. They're just associated with different cosets. So we're getting all the same stuff, just different orders of occurrence. Is there any troubles with this? This is it. We're just gonna like look at this and make some notes. And you feel okay about cosetting? Yeah, let's make things a little bit. Let's make things a little geometric. Is that bummer? What? I want new counsel.
Been fired.
That job didn't last long.
No,
Oh, God, no.
I've been through 7 lawyers just this morning.
Who's next? Is Kyle next?
Yeah, sure. Kyle, you're up.
refuses to take the job.
Not even pro bono? You're on your own, Dr. T.
It looks like it. Representing myself like, who was that maniac who just represented himself recently? What was that guy's name? He'd run through all the people in the parade. You know who I'm talking about? Woo! Makes you not want to represent yourself. Or take your meds and represent yourself. You gotta somewhere different than where he went. So this is a new group. We haven't really seen this one. It's really just the plane. So it's just the reals, crossed with the reals, and it's really all the ordered pairs, A, B, under addition. You can think of almost like a vector space if you had linear algebra, so very much like that, with less stuff happening, just the additive part. So our group operation is plus, so if we have AB plus CD, You just add component-wise. What's the identity? Yeah, identity is the origin. Beautiful, beautiful. What does a subgroup look like in here? I'm gonna run to the restroom. What would a subgroup picture? What's the picture of a subgroup in there? I'll be right back.
There's infinitely many. So fast.
He really is.
Been practicing for like 56 years. I don't want to go into the more detail.
Please don't, no, it's okay, it's okay.
I am quick. Life's too short to waste in the can.
On today's list of things Dr. T has said, I want new counsel and life is too short to waste it on the can. Okay.
All right, so there's like a lot of answers that would be right here. Do we have one subgroup you could give me?
Like a line.
Yeah,
Any of
beautiful,
them.
beautiful. Like this line, is that cool?
Sure.
Does it contain the identity?
Oh,
Nope.
no.
So
How about a line through the origin?
there, oh, so lovely, absolutely. A line through the origin. So we can just take a line through the origin, and that is a subgroup. So we can call that H equals, and let's write it really fancy. It's all x comma alpha x. Let's call it a sub alpha even.
Ooh.
Oh yeah, and you could, oh God, no, let's be more, sorry, I want to be suggestive. Racy, mathematically racy. Yeah, there's the
Oh.
third thing I've said today that's weird.
What does that mean?
I know. Zesty.
Oh.
Order pair.
Like you go,
Oh.
one of those,
Wow.
like that.
And we're done. Class is mid, friends. I'm calling it.
So, what does the M represent?
Oh, sorry.
It's okay. What does the M geometrically represent in this picture? Slope, yeah. So this is just a line of slope M. Through the origin. Cool, so we've got infinitely many subgroups. They're all the possible lines through the origin. I guess there's one that you can't write that way, and that would be the one that's on the y-axis. For that one, you'd have to just do something like that. So this would be the last line that's not included in there. That's just the y-axis. What is a coset? So let's take a point that's not, so we'll take this subgroup here. Take H sub M for your favorite M. This one, it looks like M is positive. Let's just roll with that. So take AB, it's not an element of H sub M. And so it must be off to the side. So, it is not. Yeah. What happens if yeah, well, let's come back to that, but let's just take this point off that line anywhere you want. What is the left coset? And what operation do I have here? Addition. What is this? Or a verbal description, that'll be cool too.
It should be doing A plus X.
Sure, let's write it out. Yeah, nothing wrong with that, right? That sounds like a really quite reasonable place to start. And then
Yeah.
Just shifting.
yes, yeah. So it shifts the line so that it goes through AB. Exactly. So it's just taking that line of slope M and shifting it up to go through there. Preserving slope, just moving it across. Does that make sense? So that's interesting. So the picture is a line of slope M through the point AB. So this is really very different from a lot of the stuff we've done. I like having pictures. I like geometry. I'm like some.
I felt like a slight shot.
Yeah, I know. Shade.
It's a little suspicious of you.
I'm a dicey character.
Watch yourself, Dr. T.
Growling, throwing shade around, losing 7 lawyers in a morning. Kind of a degenerate, am
Been
I?
refused by a lawyer too.
And refused by a lawyer and turned down. Yeah, yeah.
It's been a rough morning for you.
It really has. It's been rough. I didn't expect this Monday to be like this. So, if we take a different coset, let's take a different point, say CD, it's out here, then that coset is just a line of slope M through that point. What is the collection of all cosets? So first off, these are different, right? These are completely different beasts. They don't contain anything in common because they're parallel. And we know parallel lines don't intersect. What does the collection of all cosets, left cosets in G look like? Cosets of H in G, sorry. Here's another one, right? What if I draw all of them? What happens? Yeah, fill the plane with parallel lines, right? So the collection of all cosets is the collection of all lines of slope M filling the plane. And they're all disjoint. So all your cosets are just these right here. And when you look at all of them together at once, it just shades in the entire plane with parallel lines. So pretty interesting. There's infinitely many different cosets as well. Now, Sydney asked a question. She said, you took AB outside of H. What if I took AB in H? So what if I took, let's go back, draw this up again, get a fresh picture here. here was our H. That was a line of slope M. And what if I take a point on it? Yeah. And then I added, yeah, what happened? What you say? I think you got it there, Kyle. Nothing happens. Let's just prove that to ourselves. So this coset here, plus H, is just H sub M. It doesn't really change anything. It doesn't translate the line. Kind of does something weird internally to it. It moves things around, but it doesn't actually change the net effect of H sub M. Now let's see what that is. Let's see. So if AB's in there, then AB must have what form? What does AB look like? So AB in HM implies,
A equals X.
say that again?
A equals X and B equals MX.
Yeah, so A equals X and B equals MX, so B is equal to MA?
Yeah.
Yeah, so implies that this is a form.
Just what we have.
And that's exactly an element in there, right? So when you add that MA to something in here, you just get A plus X, comma, MA plus MX, and now distributive property. It's just a point, comma, M times that point. So it doesn't change anything, it's just, it literally is kind of an internal shifting of things that doesn't change it. So that's why I took it outside Sydney.
Cool.
So in a way, when you have a coset and you take something that's already in the coset and look at, or when you have a subgroup, and you take something that's already in there and multiply it on the left, you just get back the original subgroup. Let's take a look at a bunch of properties like that so that we're somewhat aware of them on page 151. And we've seen a bunch of this stuff in action already this morning. So lemma 7.1. Sorry, yeah, some folks don't have pages, right? So lemma 7.1, yeah, okay. What's that?
What a weird word.
Lemma.
It is a weird word. I always like this one too. It's not. Lemniscate, you know, they're in polar coordinates, they're the like kind of the heart things.
Oh, I know you know those.
Oh my gosh, those things.
Have you ever seen this curve? The Witch of Agnesi.
Whoa.
It's a really weird curve. I think it's something like that, or
Oh.
something like that. It's like a really cool parametric curve.
I think the coolest word I've heard in my math career is Fubini. Fubini's theorem.
Oh, you saw that in Calc 3.
Yeah,
Yeah.
like last week.
Nice. Yeah.
Just sounds like a type of pasta.
Sound
Oh, okay.
does. Wish you hadn't said that. I guess I got oranges. They don't really fit when you,
Not
when you
the
think
same.
pasta, you know?
Not the same.
Kyle's probably hungry too, so.
Kyle's already
Kyle's
eaten twice
four.
today. Kyle ate at 5, went to the gym, ate after the gym.
Wow.
Jesus.
Nice. What'd you eat? What do you eat?
Well, in the morning before I don't eat much before the gym. I just have maybe like a bagel or maybe a Cliff Bar or something. Just something to put in the body so I'm not running on
Fumes.
just body fat, which is what you run on if you have nothing in your stomach. And then afterwards, stack it with the protein, so eggs and some meats and some complex carbs.
Second breakfast, real breakfast.
Yeah, actual breakfast, yeah.
Second.
Yeah, I probably eat 5-6 times a day.
Oh my god.
I probably do too, just not as much as you. I'm always snacking throughout the day. I get a lot of shit for it.
Yeah, I mean, I just can't put on weight either. I burn probably around 5,000 calories a day if I work out as much as in season I burn probably 5,000 calories a day. So it's just
Twice a
I
day?
eat twice a day.
That doesn't sound like enough eating.
Well,
Well, I
not
mean,
saying
if you're
it's
not-
healthy,
Some
but
snacks
in the middle.
Oh,
But
you
like,
snack, okay, you snack.
yeah,
Yeah.
if I eat breakfast at like 8:40, 9 o'clock, and then I eat dinner whenever I decide to leave my room and go get dinner. I need to go grocery shopping. I need Lunchables because I do constantly have Lunchables in my room. I'm out though.
Lunchables, no.
I love Lunchables.
I'm not judging you. I just haven't had Lunchables since elementary school.
Lunchables and Capri Sun. That's what my fridge is.
Oh my god.
I'm a child.
I was gonna
actually
say,
a
yeah,
child.
I've like gone back in time.
Yeah, I know, that's.
All I have in my room is Cheerios and Goldfish, so.
What kind of goldfish? Flavor blasted?
Just regular.
Are you
Goldfish.
kidding me?
I
Those are
like
fine.
plain Jane
What's-
Goldfish.
Wait, the cheese ones? Or
Yeah,
not?
just the just the
Yeah.
regular
No, I
Goldfish.
need the
What do
flavor
you think
blasted.
she should have?
The flavor blasted.
It's too
ones.
much. It's too
Oh,
much.
it's-
I'm just trying to
it's too
snack on
much.
something.
You guys are
overwhelms
so
the mouth.
disappointing.
We're fired.
So disappointing.
Fire us.
You're fired. If you were my counsel, you would no longer be my counsel.
Have Triscuits.
That's
Oh.
like the healthiest thing I ever
That's
heard
a-
come out of anyone's
yeah.
mouth thus far.
They're so good. Get some salsa too.
Triscuits and salsa.
So good.
Like a hummus.
Yeah.
Hummus is good too. I just don't like hummus. There's something, feels like it should be warm to me and it's cold, so it kind of throws me off.
Yeah.
Okay. Oh, that's interesting. Okay.
Yeah, I need like a corn-based thing with salsa, you know? Like a corn chip or a tortilla. Something.
I just eat a lot of salsa. Put salsa in my eggs most of the time.
Oh, yeah,
Fair.
yeah. You know what I've been really addicted to lately is the crunchy chili paste. You ever had that? It's like, oh, it's so. I guess I'll bring some in when I'm supposed to make a pie or something. So,
I'm so glad he hasn't forgotten about that.
yeah.
What kind of pie do we want?
I thought it was
Oh, you-
pumpkin.
I wasn't here.
Yeah.
I
You
was
guys
the
weren't
one
here,
who-
so thank
Yeah.
goodness you're here now.
You allergic to pumpkin?
Say yes.
Am I allergic to pumpkin? No, I'm not allergic to anything.
Cool.
Yeah.
Pumpkin pie. Word.
All right.
You don't like pumpkin pie?
It's okay. I don't dislike pumpkin pie. It's just like if I had my choice of pies, I would not choose pumpkin. I would choose apple and blueberry or cherry.
I would
I'm
choose
not
an
a,
apple.
I'm not a seasoned pie veteran, so.
He's not a pie veteran. We'll learn, yeah.
Like I wouldn't have like a mincemeat. That's creepy. Mincemeat's terrible. Pecan.
See, I'm just
That's-
not
that's
had
fair.
half of these.
Can we eat pecan pie in here? Do we like? Yeah.
She
No.
says,
Okay.
"Unless-
Okay. No.
Oh,
All right.
okay.
All right. Let's stop. Let's look at lemma 7-1.
Oh, sorry.
I think this all happened when Kyle said lemma's a weird word.
Yeah, that's where it
And then we
started.
got onto pie.
Now we're on pie again. Pie has that. This is the second time we've devolved into pie conversations. So,
Yeah.
okay, cool. So let's just go through this quickly. We're not going to look at the proofs because we've seen a lot of this in action. H is a subgroup of G. A and B belong to the group G. Every element is a member of the left coset it produces. That was like the first thing I asked you, right? That's because the E is inside of H. Now, 2 is really kind of important, but also simple. The left coset produced by A is just the subgroup H, if and only if that element is in there already. So you can think of that as these cosets absorb their own elements. They just get trapped inside of there. Just like this, right? When we took something that was already in the coset, it just produced the same coset again. It didn't really change. It didn't give us anything new at all. So to get something new, you gotta move outside the subgroup. 3 is an interesting one. It gives you this idea that we might be moving up some kind of a group structure or something. It's just it's not super interesting for us right now. But I do really like 4, that if I take 2 cosets, AH and BH, they're the same if and only if one of those things is in the other coset. So I think that's a pretty good one. Now, number 5 is kind of amazing and profound, and it's going to help us knock out Lagrange's theorem. That 2 cosets, there's only 2 possibilities. either your cosets are equal or they're completely disjoint. That's the only things that can happen with cosets. So we get these pooling of things. Remember how we've seen like the same cosets appearing over and over again, and we group them together, oh, it's the same thing. And if they weren't the same thing, then they were totally disjoint. They never shared any elements. Think of all the cosets in the plane corresponding to that line. They're either the same or they're completely disjoint. Does that make sense?
Yeah.
Yeah, saw it earlier too. I mean, it makes sense. All of them are just offspring of the same piece here.
Indeed, yeah, absolutely. And so number 7 is kind of the last one I want to look at for right now, that all cosets have the same number of elements. And we've seen that. Yeah. So the order of AH is order of BH. Same number of things, which kind of makes sense, right? You're just taking A times everything that's in H, so you're just kind of permuting things inside there. All right, let's talk about Lagrange's theorem, and let's look at it in a very different way. I don't want to use the proof in the book. I want to give you an intuitive proof. And we'll lead ourselves up to Lagrange's theorem. I don't even want to state it. I just want to start talking through this picture that I had up earlier. So we have got this group G. We usually don't get the chance to draw pictures in this class. So today's a very picture-laden day. So I've got this group G. That's the whole thing in that rectangle. And then I've got a subgroup H. So here's a subgroup H, proper subgroup, and it's got the identity inside of it. It has to, that if it's a subgroup, it has to have the same identity as G does inside there. So now let's take some element that's not in there. I'm going to take, I'll just kind of write this up a little bit. I'm going to take G1 that's not an element of H. And I'm going to produce that coset that corresponds to it. So E times G1 is going to give me G1. And then everything inside H is going to get multiplied by G1 on the left, and it's going to produce this left coset, G1, G1H. Those share nothing in common, right? Because this is this coset, EH. This is the new coset, G1H, and by the property, which property is it? I guess 4, property 4. I know that those have to be different. They can't be the same. And I also know that, they're totally disjoint. So now take a G2 that's not in here. And I'm going to multiply that by H. And I now have a new new coset, G2H. So now check out what's actually happening to, I guess that would be, that would just be G2 times E. So I've got this whole new coset. None of this stuff is the same. None of it shares any elements. By the way, I'm producing this in the properties we just took a look at. So let me just stop really quick. Is this making sense, this construction? And so I keep doing this. Let's also assume that the order of G is finite. So nice finite order. We're going to run out of stuff. So now do G3 that's not in here and produce that subgroup. So I've got G3H, and I'm going to do this repeatedly over and over again until I just run out. Let me trim that up, make it look a little bit nicer. There we go. So I've got G4H, G5H, 6, 7, 8, 9, 10, 11, 12, 13, well, wait. Yeah, 14. Okay, that's okay, because I started with 0. Okay, that got a little scary. Here's G13H. And so I've got all these subgroups, not subgroups, these cosets. What do I know about the size of each one of these little squares? The number of things that are in each one? Same, yeah. So there's the same number of things. So the order of G sub I, H, is equal to the order of G, J, H. no matter what I and J are. So we've got that. What is the index of H and G in just this picture?
Just do
15, exactly. And so now all these things are distinct. They all have the same number of elements. So for this picture, it's 15, but let's just pick a nice general thing here. Let's call it K. So I'm gonna write something out here. Since all of these are disjoint and have the same number of elements, the total number of elements in each one times the number of cosets is going to give me the order of G. Well, first off, we must have all elements of G covered by some left coset. So everything that's in G eventually will be inside one of these things. And if the order of G is n, and the index of H and G is K, sorry, I'm trying to think of the right words to say this. So, were you saying some words, Kyle?
I think I know where you're going, but I'm just guessing.
Okay, what were you saying? What was your guess? Because maybe you have some beautiful words for it.
Well, were you going along the lines of the element? The number of elements in each one of those cosets is what, n divided by k?
Yeah, exactly, yes, yes. So, so we have K equal cosets. We have a total order of n for our big group. And so, and all elements accounted for. So K, the number of cosets, times the index, yeah, that is the number of cosets, times the size of H, because all those also have the same size as H, right? So that's actually all the same size. They're all the same as that original subgroup that I started with, equals n. So this is the order of the group. This is the number of cosets, and this is the size of H. So this is actually K times order. Let's actually get some better notation. The index of H and G times the order of H equals the order of G. And so, Kyle, I like the form you gave it in, that there's a couple ways to say this. So Lagrange's theorem says that the order of any subgroup divides the order of a group. So the order, let's write that out as a sentence. The order of any subgroup divides the order of the group. And we need these cosets to see that. And then furthermore, the number of cosets is equal to the order of the group divided by the size of the subgroup. And that's really just Lagrange's theorem. Now, I want to point out a couple of things here. This doesn't go the other way. Just because you have a number that divides the order does not mean you have a subgroup of that order. So note, just because a number divides the order of the group does not imply there's a subgroup of that size. goes one way only. And we'll put some use to this on Wednesday. But I kind of actually want to give you a few problems just to do, just like a couple before Wednesday. And maybe make this due on Wednesday, it's just like a couple things, too, just very tiny things. So that we just get some practice with this. More practice finding cosines. So super, super small. So chapter 7, let's just, if we can get this on Wednesday, and I think you can do these, this should be okay. If you have any questions, email me. But I was just thinking, problem 4. And maybe we won't even go any crazier than that. Let's see here. I think we actually did 1 already. I think we did that kind of last week. Or maybe didn't we do that number 1? Page 163, or problem 1 in chapter 7? It feels like we did that together.
It's something like that. I don't know if it's exactly that, but we did something like that.
Okay. Could we, actually, so how about this? Could we do 3 and 4, and that's it? Nice, simple, early problems. And that's it. All I need from you. It's really all just computation. Does that sound okay?
Yeah.
Okay, wonderful. And maybe try to get those to me at the beginning of the hour. And, that's it for today. Nice, tiny assignment. So, I got some stuff to get back to you from last time, too. And I don't think I've got some stuff I owe you still. But I don't think I got what chapter was this one? Chapter 6?
This is chapter.
Did I get that from you?
2.
Okay, awesome, thank you, beautiful. Yeah, I'll take that from you. Could you just fix this up? for me
Yeah,
and
I
get
was
it to me?
gonna ask about that too. I saw
Yeah,
this morning.
and I'd be happy to like just, give you those back, but just
Okay.
add those things, sir.
Yeah,
Thank
will
you. By whenever, by next Monday, tops.